Hi, my name is Shaun Lahert and this is my presentation for Price's Summer of HPC. The project was on searching for excited states of the nucleon in lattice QCD at the physical point. The excited states of the nucleon with spin 1/2 are listed in the table below. These are short-lived particles with the same quantum numbers of the nucleon. Total isospin 1/2 is the defining quantum number, which means the particles are all composed of either 2 up and 1 down quarks or 2 down and 1 up quark. To simulate these states on the lattice, we require nucleon interpolating fields with the correct isospin and spin. We choose 2 different operators with these properties. The correlation function of these operators then gives the probability amplitude of a state with the correct quantum numbers existing on the lattice. All excited states contribute to this amplitude with an effect related to their energy. The correlation function is then computed on the lattice by Monte Carlo methods applied to the path integral. The specific simulation parameters are shown in the table. The pion mass, being 135 MeV, is special as this corresponds to its real physical value. This is relatively new in lattice QCD, as a lower pion mass means more computation. What is also unique is the number of configurations, as a typical simulation would only contain a couple of hundred of configurations. From the simulation, we have a large amount of samples in the form of the 2x2 correlation matrix pictured. Due to the periodic nature of the lattice, we have backwards and forwards time correlations. The positive parity states going forward in time correspond to the negative parity states going backwards in time, and vice versa. Also, due to the exponential dependence, the ground state dominates at later times, and the excited states are all contained in the earlier time slices. The generalized eigenvalue problem is the standard method of extracting the energies from the correlation matrix. The eigenvalues contain the energies, and the lowest states can be extracted by a plateau fit of the log of the ratio of the eigenvalues at consecutive time slices. Pictured is a plateau fit for the positive parity channel for the 2 eigenvalues. The proton is clearly visible at 940 MeV. The excited state plateau, however, does not seem to correspond to any obvious single or multi-particle state, but the data is too noisy to do an accurate fit, in spite of the large number of statistics. A double exponential fit of each eigenvalue shows a good agreement with the plateau fits. For the negative parity channel, our ground state does not seem to correspond to any known state, but again the data is very noisy. The first excited state, however, does lie within the region of the N1650. AMIAS is an alternative approach to fitting correlation function data. It uses a chi-squared fit function to weight each set of parameters. Then, using Monte Carlo methods, we can sample the parameter space to generate probability distributions for each individual parameter. These distributions will be Gaussian for large enough sample sizes, and we can determine the best fit parameters and the errors from the properties of the Gaussian distribution. Pictures are results for this method applied to our positive parity channel. There is a strong agreement between these results and the GeVP results, with the ground state of the proton being clearly resolved. From our second amplitude plot, we can also see that our second nucleon operator has very little overlap with the excited states. To conclude, although the proton was resolved very clearly, other low-lying states did not show up in the data. A large number of configurations at the physical point does not guarantee a reduction in errors. Going forward, alternative simulation configurations must be considered in hadron spectroscopy on the lattice. Also, multi-particle operators may be needed to properly resolve multi-particle states with the same quantum numbers. I would like to thank Price for giving me the opportunity to work on this project. I would like to thank my advisor Konstantia and also Yanis and Jakob for helping me throughout my work. And finally, thank you for watching.